Hey, freshman. It's Tuesday, the 31st of March, and this is lesson number 3. We're just moving right along here. We left off with a question. When Billy Bob throws those rocks overboard and they fall to the bottom of the pond, the question is, what happens to the level of the water on the pier? Does it go up? Does it go down? Or does it stay the same? I hope you thought about that overnight, because we're going to do that for you right now. By the way, Archimedes' principle keeps that boat to float. Bernoulli's principle allows a sailboat to move forward in the water with the wind, into the wind. Think about that. We'll talk about Bernoulli later on, but that's Archimedes' principle, what we're studying right now. Okay, so let's go ahead and take some water, put it in one of these beakers. And then we're going to go ahead and float a boat with some cargo in it. Big old boulders, Billy Bob boulders. Yeah, I put 10 of them in there, just like before. I'm going to go ahead and float it in there. I'm going to add a little bit more water. Bring it up to the top mark of that beaker. Okay? I'm going to take a marker and we make it really evident where this starts out. Right there on that line. You can see that, right? That's the water level. Now let's go ahead and take the pennies, the boulders, and we're going to throw the boulders into the pond. Whoop. We're going to float the boat again. And for those of you that said that the water level goes down, you were correct. Let me get that level right there. The water level went down, and here's the reason. Because the density of copper, not copper, well, copper for this demonstration is, let me look here, 9. What does that mean? That the density of copper, in the case of this, the boulders, is 9 grams for every 1 cubic centimeter. And grams is weight. And volume is size. So look at the number 9, compare it to the number 1, and you see that these copper pennies weigh more than they are big. And so when they're in the boat, they displace their weight. But when they're in the water outside the boat, they displace their volume. So which has more influence on the water? When they're displacing their weight in the boat, or when they're displacing their volume when they're in the water? So these are heavier than water. They will sink, and that's why that water went down, because they have less influence when they're in the water. And don't forget, you have more influence when you're in the boat. And the boat's name, as you know, is Jesus. Okay, stay in the boat. Serve him all the days of your life. We're going to erase that and go to our next lab topic. I'd like for you to look at this lab sheet again. Again, if you don't have it out, go ahead and go get it. Stop the film. Now we're going to go to the summary. A floating object displaces its weight in fluid, and a sinking object displaces its size or its volume in fluid. But in both cases, the weight of the fluid displaced equals the force of buoyancy pushing up under the object. And you can see that if the size is smaller than the weight, there's not much buoyancy pushing up underneath, because when it's in the water, the size is what's being measured. Okay, now we're going to go ahead and do labs C and D. And the way you do that is you flip this thing over. I've made them nice and big. They're back here. These are C and that's D. So we're going to take away the clay, make our own little boats now. We're going to weigh this clay right here, molding clay. That digital balance on 25.81. So the weight of the clay is 25.81. Let me draw the picture here. Here's the overflow can. And the weight of the clay is on the top in the air. And it weighs 25.8 grams. Now it says to prime the overflow can, and we'll do that. By now you should know how to prime an overflow can, so if you ever get a chance to do it again, if we ever get back together in school, that'd be fine. While it's priming, let's see what's next. Make a boat. So we'll take that wad of clay and make a boat out of it. And the way I do that is I push down and pull up on the sides. Push down and pull up. It's kind of like making a little teapot, short and stout. Here is my handle. Here is the spout. And then there's something more to it. I can't remember what that is. And so now we have this thin-walled, deep, sided boat. Now that clay still weighs 25.8. It's just shaped differently. All right, and it says put the boat gently in the water. But I'm going to make sure I throw away the overflow. Otherwise, that'll mess things up. Now, what did we decide we were supposed to see here? Well, if this floats, and it should, then if this thing weighs 25.8, you would expect 25.8 grams of water to overflow, and you would expect 25.8 to be the buoyancy underneath, the buoyant force to be 25.8 grams. Notice we're not changing things to newtons, because grams will be just fine since we're still working on the surface of the earth. Make sure that that's good, and it is. So we're going to lower it down in there very gently. And we'll get our 50 milliliter graduate. And this is density of water is 1 to 1. 1 gram for every 1 cubic centimeter. Wow. We were expecting 26. We got 26. Let me get that straight. There you go. So we got 26 grams, 26 milliliters, 26 grams of water that overflowed. So what can you tell me? That was 26. And what does Archimedes say? Archimedes says that this should equal this. That is Archimedes' principle right there, that blue thing. That the weight of the fluid displaced by an object immersed in the fluid is equal to the buoyant force underneath it. Now, if it's a floating object, they're all three going to be the same. The weight of the object in the air is going to equal the weight of the water that overflows, which is equal to the buoyant force underneath. Now let's make it into a clay ball. And it says to roll the clay into the ball. So at this point, you guys are getting to be experts. You should go into nautical engineering, build boats. Okay, so we're going to go ahead and prime this thing. Borrow some water from over here. Okay. And this time we're going to roll it into a ball. And we're going to drop the ball in. Now, when it's a ball, does it still weigh 25.8? Yes, it does. Let me make this into, do you think that the water that overflows is going to be the same as it did when it was floating as a boat? 26 grams? Let's find out. You expect it to be greater than 26, less than 26, or equal to 26? Let's find out. Here we go. Well, don't forget, when an object floats, it displaces its weight. When an object sinks, it displaces its volume. Is clay a density greater than 1? Well, it sunk down in there, then it must have a density greater than 1. So what are we going to get? Are we going to get the weight of the clay, or are we going to get the volume, the size of the clay? Well, if the clay's density is 2, let's say, then it weighs 2 and a volume of 1. Every volume of 1 cubic centimeter weighs 2. Let's find out. Here we go. It is 15, 16, 17 milliliters. 17, here, let me turn it for you, milliliters. Okay? So there's 17 milliliters that overflowed, which equates to 17 grams since it's water. And so that's the force due to weight of the water, 17 grams. And therefore, the buoyant force must be 17 grams according to Archimedes' principle. Because 17's got, these have to equal one another according to Archimedes. But do they equal 26? No. So how much does the clay feel like it weighs when it's in the water? Well, take 25.8 minus 17. 25.8 minus 17, and that would equal 8.8. It feels like it weighs 8.8. It's called the apparent weight. The apparent weight is 8.8 grams. And you just simply take 25.8 minus 17, which is pushing up. Pushing down compared to pushing up. So you take 25.8 minus 17, and you get, it feels like it weighs 8.8, the apparent weight, 8.8. So what are you telling me? I'm telling you that if you sink in water, there's a buoyant force pushing up underneath you, but not enough to make you float. Some people have big bone density and they can hardly float at all. They just sink right to the bottom as soon as they jump in. I'd like to calculate the specific gravity of the clay, or what's called density. Specific gravity and density are the same numerical value. So how did we get that? Well, isn't the density equal to the weight in the air divided by the loss of weight. So it is this divided by this. Not this minus this that gives us our apparent weight, but this divided by that gives us our density. And so what is 25.8 divided by 17? Well, let's find out. 25.8 divided by 17. It's 1.5. I thought it was around 2. So the density is approximately 1.5 grams for every cubic centimeter. That's why it sunk. I grew up near a river, so I got my bath. And I would lift up rocks from the bottom of the river, and I would lift them up. As soon as it broke the water line, they really got heavy. And it's because I lost that buoyancy that was underneath the rocks. All right. Archimedes Principle is on the bottom of this sheet. The buoyant force on an object is equal to the weight of the fluid displaced by the object, and that's whether it is sunken or floating. It doesn't matter. Either way, still the same principle. And now we're going to go over to E. Weigh the beaker with some water in it, then weigh a wad of clay. So we're going to go ahead and weigh the beaker with some water in it. On. And it says 229.7. 229.7. All right, now when we put this in there, and this weighs 25.8. Fifteen, 5. Will the weight showing on there be 255.5, more than 255.5, or less than 255.5? When you put this, and then you put this inside into it, will it weigh the same? Will it weigh less? What do you think? Let's try it. You're going to have to trust me. 255.5. Exactly. All right. And then make a boat. Is the combined weight still the same? And the answer to that is going to be yes. You say, well, I don't understand that. Well, think about it tonight. Now, next time we meet, we're going to go into this thing called Pascal's Principle, where you can use a hydraulic lift and lift up elephants with a simple little small force pushing down on a piston. Well, it's been great being with you guys again today. God bless you. Have a great day in paradise.